Welcome back. I'm absolutely pumped for today's explainer, because we're doing a deep dive into the production of water for injections. It's something you've definitely interacted with, but let's be real, probably never given a second thought. We're going to explore the surprisingly complex, highly engineered, and just intensely regulated world of medical-grade water. Let's get into it.
So when you think of life-saving medicine, your mind probably jumps to complex chemical compounds or, cutting-edge biologics. But what's the most critical yet completely overlooked ingredient in all of that? It's water. Specifically, the water that acts as the carrier for drugs injected right into your bloodstream. And as you're going to see today, the production of this water requires literally insane levels of engineering.
Now, a really crucial point up front. We are not talking about standard tap water here. Actually, we're not even talking about the fancy purified bottled water you might drink after a workout. We're looking at what's officially called water for injections, or WFI. This is a highly regulated, intermediate bulk pharmaceutical ingredient. It demands the absolute highest pharmacopoeial quality. Why? Because the margin for error when injecting something directly into the human body is, well, it's exactly zero. There's no room for mistakes.
Here's our roadmap for today. First, we'll look at why it's more than just water. Then, the methods of purification. Next, storage and distribution. And finally, the ultimate water test.
All right, part one, more than just water. You know, water is actually the most widely used raw material in pharmaceutical production. It's the universal solvent. But because it's so incredibly good at supporting life, it's also a massive breeding ground for relentless invaders. I'm talking about microbes and the highly dangerous cellular debris they leave behind, which are called endotoxins or pyrogens. If everyday water, full of these invaders, gets injected directly into the bloodstream, completely bypassing our body's primary immune defenses, it poses a severe, even fatal biological danger. So these invaders absolutely must be stopped.
And to combat that exact danger, the World Health Organization stepped in. They've established this massive, totally rigorous regulatory framework of good manufacturing practices, specifically tailored for water intended for pharmaceutical use. These guidelines dictate exactly how this water has to be designed, produced, stored, and constantly, and I mean constantly, monitored, all to guarantee those microscopic invaders never, ever make it into a patient's medicine.
Moving right along to Section 2, Methods of Purification.
So for the longest time, there was pretty much only one accepted way to produce water for injections, and that was distillation. It's the traditional gold standard. Basically, it's a super robust phase change method. You boil the water into steam to leave all the impurities behind, and then condense it back into liquid. But modern guidelines have evolved, and they now allow for other advanced means. We're talking techniques like double-pass reverse osmosis coupled with ultrafiltration, or even electrodeionization. These modern systems are wild. They use high-tech membranes and electrical fields to strip the water of literally every single impurity.
But wait, this intense production process doesn't just start from a muddy puddle. The feed water prerequisites are already incredibly strict. Before the extreme purification even begins, the source water must already meet strict potable drinking water standards. I mean, it has to be supplied under continuous positive pressure in a totally defect-free system. It goes through initial filtration and softening just to be deemed worthy of entering the water for injections purification plant. It's a VIP club for water, for sure.
Okay, Section 3, Storage and Distribution.
Now, what's really interesting here is that purifying the water is actually only half the battle. Once it's stripped of everything, it becomes highly susceptible to recontamination. So look at this temperature requirement, greater than 70 degrees Celsius. That's over 158 degrees Fahrenheit. To stop microorganisms from growing back in this perfectly pure water, it's often kept constantly circulating in the distribution loop at literally scalding temperatures. It creates an incredibly hostile environment for any bacteria trying to set up camp.
But get this, temperature isn't enough. The water also has to move. Think of the piping system as this high-speed, scalding highway. Engineers designed these systems to maintain a continuous, turbulent flow. The water is never, ever allowed to stop moving, because if water stagnates, bacteria can adhere to the pipe walls and form these dangerous biofilms. By keeping the flow turbulent and totally eliminating any stagnant branches, which the industry calls dead legs, microbes literally can't get a grip. They're just swept away.
And the physical design of the tanks and pipes, it's a total marvel of extreme storage engineering. They use this very specific, highly corrosion-resistant material, 316L grade stainless steel.
Everything has to be perfectly smooth. The tanks use sanitary bursting discs for pressure relief. And inside the storage vessels, they actually use spray balls to continuously wet the headspace, that area of air above the water. Why? Because even a tiny dry spot could harbor bacteria. The golden rule here is simple: absolutely no dead zones.
It goes so deep that even the air entering the tank as the water level drops has to be engineered. They use hydrophobic, bacteria-retentive vent filters. These filters basically allow the tank to breathe, letting air in and out as the liquid levels fluctuate while completely blocking any microbial contamination. Oh, and to prevent water vapor from condensing and blocking those filters, they're often actively heated. I mean, they've thought of everything. Every single vulnerability is covered.
Which brings us to Section 4, the ultimate water test.
Look, you can build the most advanced system in the world, but in the pharma industry, if you didn't document and prove that it works, it didn't happen. So before a single drop of this water ever touches a patient, the entire system has to survive this grueling 3-phase validation process that takes a full year. Phase 1, that's 2 to 4 weeks of intense, daily testing of every single step in the process just to establish operating ranges. Phase 2 is another 2 to 4 weeks doing the exact same thing, but this time it's entirely run by the regular operators using the finalized standard operating procedures. And then comes Phase 3, 1 full year of continuous monitoring. This is to prove the system works flawlessly across all seasonal variations of the incoming feed water. It's intense.
And the craziest part? Even after that year-long validation, the monitoring never actually stops. You've got this continuous technological surveillance. Online instruments are constantly monitoring flow, pressure, temperature, conductivity, and total organic carbon, which is basically checking for any biological matter, all in real time. If anything slips even a fraction, alarms go off. But they don't just rely on tech. They also do rigorous manual testing for endotoxins. They use specialized techniques like the LAL method, which, fun fact, is a test that actually utilizes the unique properties of horseshoe crab blood. It really is just this relentless pursuit of uncompromising quality. So, that leaves us with one final thought. The next time you're at the doctor's office getting a shot, are you just going to think about the medicine? Or will you be thinking about the scalding, turbulent, hyper-engineered, and year-long validated journey of the pure water carrying it into your body? It really changes how you view a simple medical injection, doesn't it? Thanks for hanging out with me for this explainer. Keep asking questions, and I'll catch you on the next deep dive.